So the last time, if you recall, we were discussing what's called the reconnection rate, somewhat paradoxically called the reconnection rate. It's really the reconnection velocity, this thing, right, which is essentially the velocity at which the two oppositely directed field lines, are being forced to meet, if you will. Okay, and the velocity at which these two oppositely directed field lines are forced to meet determines the rate at which magnetic flux is eaten up or annihilated in the small reconnection region right here, right. So this is what we were discussing the last time, and we saw that the steady state reconnection rate or the reconnection velocity goes as VAI divided by VAI being the alphane speed. This is the alphane speed in this region essentially, or in this region, not in the reconnection region. Okay, so that's what it means. In other words, the alphane speed in the undisturbed fluid, if you will, the alphane speed in the region of the fluid which is not being subject to reconnection. Okay, so reconnection being a microscopic phenomena, there is little hope of observing it directly, except of course in lab situations, and we will talk about that a little bit. There are experiments such as the magnetic reconnection experiment, the MRX experiment. I urge you to Google it, MRX. Okay, and experiment. So in such experiments, of course, it's possible to actually, stick a probe into, the so-called reconnection region and figure out the actual geometry of where exactly the reconnection is happening and do wonderful things like that, right? The trouble is in these lab experiments, the conditions, it's very difficult to achieve the kinds of very high Reynolds numbers that are often thought to be encountered in astrophysical situations. So while they are instructive, they're not quite the same. All right, so that's one thing. The other thing is, of course, in astrophysical situations, you're not really probing the reconnection region per se. What you're probing is a very indirect quantity, which is the byproduct. And I emphasize this, what you're really probing is in astrophysical situations, one probes the byproduct of energy released due to reconnection or in the reconnection process. This is what one really probes. So you see, first of all, most of the time, it's not just one reconnection episode, it's many reconnection episodes. So probably many episodes. In other words, there are many firecrackers going on, episodes of reconnection. And one typically does not have the time resolution to resolve one episode by another. More or less sort of averages over several episodes of reconnection. That's one thing. Secondly, so the energy is released, we more or less comfortable with that. That's one thing. But what is actually observed in astrophysical situations is a byproduct of the energy released, which is the radiation released. Okay, so the energy released in reconnection episodes heats up the plasma, and the heated plasma emits radiation, and that is what you observe in astrophysical situations. So I want you to be very clear that when we talk about reconnection in astrophysics, we're not really in a position to probe the actual physics of the reconnection. We are really investigating very, very indirect effects. Okay, at any rate, so the reconnection rate is generally taken to be this, and it is related with the alphane speed in the non-reconnection region, in the bulk fluid, by this relation. But R sub m is the magnetic Reynolds number. Okay. Now, as we know, it is suspected, it's generally suspected that the magnetic Reynolds number in astrophysical plasmas is very, very large. Okay, it tends towards infinity. I mean, numbers range from 10 raised to 4 to 10 raised to 6 to even more. Okay, if you look up the definition of the magnetic Reynolds number, you'll see that the resistivity appears in the denominator. So the smaller the resistivity, the larger the magnetic Reynolds number, and that's often the case in astrophysical situations. So what this means, what this essentially implies is that because this is very large, the reconnection velocity or the reconnection rate is considerably smaller than the alphane speed. Okay, so now let us also be very clear about that. Okay, what does one really mean by reconnection, or rather in astrophysical situations? Okay, what does one really mean? As in, it's not as if we are able to probe the reconnection region in astrophysical situations. It's not like that, right? So what one really means is that, like we said, we are really observing the byproducts of reconnection. So we are really observing radiation, and this is something we discussed the last time also, and I want to radiation flux. So what one really observes is something like this. Okay, say a radiation flux as a function of time, and one in a solar flare, for instance, at some particular wavelength, say X-rays or sometimes gamma rays, but ultraviolet or even lower energies or longer wavelengths like the radio, a typical light curve would probably look like this. Something with a very sharp rise. Okay, it's not really vertical, it's just that it's a relatively slow decay. So many times you have access to this. You have access to some kind of a full width half maximum kind of quantity, and this would be observed time scale. This is really the only observational quantity that you have access to. And then one uses this T-obs. You use the T-obs together with some estimate, with some reasonable estimate, with some estimate of a length scale, of a length scale. And what do you mean by the length scale? Well, some guess about the length scale over which you think the reconnection is happening occurs. Okay, so you use T-obs and L to get some kind of a V reconnection. L over T-obs would give you V reconnection as demanded by the observations. So this is one thing. Okay, so you realize that this V reconnection is a rather indirect thing. First of all, you are thinking you're thinking that this is most likely not the byproduct of one episode of reconnection. This is most likely the byproduct of several episodes of reconnection. Number one. Okay, so what you're really seeing is an average effect due to several reconnection episodes. Okay. Number two, you also have to have some idea of a length scale, and in some situations like in the solar corona, you do have some access to imaging, and so you have some idea of the length scale, and from that you get a V reconnection as demanded by the observations, and you compare V reconnection with V alphane. Now, in order to, do you have any idea? I mean, how much, rather, a fairer question to ask would be, how much of an idea do you have about VA? Because the VA, you see, is you need to know the magnetic field and you need to know the density. I think this is 4, maybe not 8, it's probably 4. So, so how much of an idea do you have about the magnetic field in the region that you are interested in? You have some very indirect estimates. Both about this and this, you have rather indirect estimates. But nonetheless, those indirect estimates are the best we have, and therefore you have some indirect estimate of the Alfvén speed. Okay, so what you then do is you compare the reconnection speed, the observationally demanded reconnection speed, which, as we said, is obtained rather indirectly estimated Alfvén speed, and then you see that often we see that V reconnection is not too different from V Alfvén, maybe 0.1 or 0.5 times V Alfvén. I say maybe because everything is a little uncertain. Our estimate of V reconnection is a little uncertain, our estimate of the V Alfvén is uncertain. Okay, but at any rate, we generally in astrophysical situations, it's generally observed that the reconnection, the demanded reconnection speed which is mandated by the observations, is not too different from the Alfvén speed. Whereas, what do we have here? What do we have from the reconnection rate as predicted by the Sweet-Parker model, the model that we saw the last time, this model. Okay, the reconnection rate predicted by this model as discerned from these 3 equations is that the reconnection rate is considerably smaller than the Alfvén speed. Okay, the reconnection velocity is considerably smaller than the Alfvén velocity because the magnetic Reynolds number is much larger than 1. Right. So this is what I mean by saying that this is not what the observations mandate. So it took us a little while to sort of understand what this sentence means, not what the observations mandate. Okay. So now what do we do? Okay. Well, Petscheck in 1964 proposed a rather unique solution. What he said was what you do is there's a thickness of the reconnection region and then there's a macroscopic length of the reconnection region. What he said was, if we can find some way of reducing the length of the reconnection region like this, in other words, so the reconnection really happens here, just here, okay, not over the entire capital L. Okay, so the thickness of the reconnection region is of course this. Okay, but what you do is the reconnection geometry is now altered. Okay, so that the reconnection is really happening over a much smaller region whose lengths, whose dimensions are now L star. Okay, the reconnection occurs over L star, not L. Where L star, this length scale is considerably smaller than L. Okay, so that everything else pretty much remains the same. You've got the V, you've got the electric field pointing out of the plane of the paper and so on and so forth, and you've got the the oppositely directed field lines being pushed in at a rate Vi, which is of course the rate at the velocity Vi is of course governed by what goes on in this region naturally. But then the only thing is, instead of this kind of a geometry, the geometry is slightly altered like this. Okay, there's an angle alpha, and so the reconnection is actually happening only over L star. What happens then? So what happens is these standing shocks out here, what happens is, you see, even in the Sweet-Parker scenario, we saw that after reconnecting, the field lines kind of snap apart, they snap apart. And in doing so, they drag the fluid. I mean, because of the speed at which they snap apart, the fluid flows quite fast in this direction and that direction. And often the speed at which the fluid flows exceeds, some characteristic speed. And we know that there are several characteristic speeds in magnetohydrodynamics. There's the Alfvén speed. Well, there's a sound speed, of course. There's a sound speed, there's an Alfvén speed, there's a slow magnetosonic speed, and then there's a fast magnetosonic speed. It is generally believed that the speed at which these flows happen exceeds the slow magnetosonic speed, okay, and therefore there's a possibility of standing shocks, slow mode shocks occurring here, okay, and so these shocks kind of create a wedge in the flow, okay, and make it so because shocks cannot occur over these entire, the extent of these outflows is limited, okay. These outflows are not happening all over. These outflows are happening only over a limited region. Therefore, the shock can occur only over a limited region, like this, okay. Therefore, that naturally creates a wedge-like geometry, okay, and that naturally makes the reconnection region like this, So, they wedge the flow and the current sheet is now miniaturized. So, it's almost like a mini Sweet-Parker system. Why mini? Because the reconnection is not happening all throughout the macroscopic dimension L, but only over a smaller length. Okay. Now what happens is, if you do mass conservation, okay, mass conservation now gives you this. Instead of the L star, instead of, when we last wrote down mass conservation like this, we wrote L here instead of L star. Now we have L star. Okay, all right. Now you see, the thing is, if the the L star is almost equal to the thickness of the reconnection region, then you see the VI can be almost VAI, as quote unquote mandated by the observations. That's what we said here. You remember, often we see that the V reconnection needs to be almost about the V Alfvén speed. And that seems to be kind of, the Petscheck kind of geometry seems to satisfy this, as long as the macroscopic dimension, the quote unquote macroscopic dimension, is almost of the order of the microscopic one, of the thickness of the length current sheet. In other words, if this thickness here is about the same as this. Okay, now that's quite a demand, really. Okay, that's also a little unrealistic, but at any rate, if this can happen, the reconnection rate can approach the Alfvén speed. So this is one, this is one thing to consider. Unfortunately, although this is a elegant solution, this is not thought to be the case. This is not thought to occur for various reasons. Okay, because at least in simulations, one cannot, even in lab experiments, it's very difficult to actually image the reconnection region, but one can do very detailed computer simulations. And in simulations, it is often observed that the geometry of reconnection is more like Sweet-Parker, is more, there's a very small dimension and there's a large dimension. It's not so much like Petscheck, where both the dimensions are about the same. You see, in order for VI to be approximately equal to VAI, the small l has to be about the same as L star. In other words, the two dimensions, need to be about comparable. And that's often observed to be not the case. Although this is one elegant, easy, way out, unfortunately, it just remains as that, and that's not observed to be the case. Although I must say that the last word has not been said about this. This is still a very active, ongoing area of research. Okay, so now let's move on to more practical issues. So why are we interested in reconnection at all? Is because of the energy released in reconnection, because reconnection is a means of extracting magnetic energy, as we said, in small bursts, in small episodes. Okay, so the energy released due to reconfiguration of magnetic fields is conceptually appealing. The excess energy over and above the minimum energy or potential energy configuration, as we've said, that is stored in the twisted fields is released during the reconfiguration, and this kind of energy release is held responsible for a variety of phenomena, from solar coronal mass ejections to solar flares. When we meet next, I'll show you nice pictures of solar flares and also of coronal mass ejections. Okay, so this will give you a good real feel for the astrophysical context of this energy release. Also all the way to flares in active galactic nuclei, not just the solar corona but extragalactic situations. Okay, to phenomena near the geotail on the night side of the Earth, where the whole point is that the Earth is continuously being impacted by the solar wind, and so there's reconnection happening in the front on the day side as well as on the night side, and there's energy release there, and in these reconnection regions in what's called the geotail, and this has been measured in great detail by near-Earth spacecraft. So reconnection is held responsible for this wide variety of phenomena. Okay, and the thing is, because you have these electric fields anywhere, whether you're talking about Sweet-Parker reconnection or this reconnection, there is an electric field here. That's unavoidable. When you've got oppositely directed magnetic fields coming together, you will have an electric field induced. Okay, and that electric field accelerates particles, right? You've got an electric field, and the electric field will accelerate particles. Okay, and we are talking particles because by the time you are down to length scale that are small enough, as small as the reconnection region, the fluid approximation almost breaks down, and so you are really holding a magnifying lens to what's going on, and you are almost sort of observing the particles, so to speak. Okay, the dimensions of the reconnection region are so small that they what's in there, you cannot use a fluid approximation anymore. So you're justified in starting to talk about particles, and these particles can be accelerated due to direct electric field acceleration in the current sheet. The force on a particle is just you know this from elementary electrodynamics. Wherever you have an electric field, there's a force, right? And so there's a force on the charged particle, and so the force causes the particles to be accelerated, and accelerated particles, they emit radiation. So there is direct particle acceleration. There is also stochastic interaction with eddies in the turbulent reconnection outflow, and so we will talk about this in a minute in some more detail when we meet next. Let's put this particular aspect off for the time being. So the point is, this is the reason reconnection is appealing. Okay, there's plasma heating, there's also particle acceleration, but at the end of the day, all of this energy is essentially how much energy you can extract from the magnetic field. Okay, the magnetic field carries excess energy, and when it relaxes to a lower energy state via cutting and pasting, which is reconnection, via the process of reconnection, some of that excess energy is released, and how much of that excess energy is pumped into various avenues depends. Okay, and these are the avenues that are of interest to us. Now, exactly how much excess magnetic energy is released, of course, depends upon the reconnection rate, right? So let's talk a little bit about the reconnection rate. You see, field lines are annihilated, or they are eaten up at the X point in the reconnection region. So at least in one dimension, measure of the reconnection rate is simply the rate of change of magnetic flux, phi dot. Okay, shall we say this phi dot is just phi dot is essentially shorthand for d phi dt. Okay, there's Gauss per centimeter square per second, at least in CGS. Okay, so let the extent of the reconnection region perpendicular to the plane of the paper be given by L, in this case please replace paper by screen. Okay, let B sub I be the average field strength in the quote unquote reconnection region, and let the inflow speed be VR, like this, like this. Okay, now we are changing notations a little bit. Don't worry about that. Okay, so then if that's the case, then this phi dot is Bi times L times VR. And you can figure this out just from dimensional considerations as well. All right, what about it? So now the quantity VR is what we were discussing about for the most part in this lecture, and that is the all important reconnection speed. How much of a fraction of the alphane speed is it? That's what we were worrying about. Whatever it is, okay, it's all important reconnection speed, okay, often called the reconnection rate. It's a bit of a misnomer. At any rate, now various reconnection theories predict numbers for VR, and the issue is to account for observations which predict fast reconnection rates that are close enough to the alphane speed. Reconnection speed that are close enough to the alphane speed. Okay, that's what's called fast reconnection. And I would say a reasonable popular guess in astrophysical situations is this. Okay. The reconnection speed is something like 1/10 of the alphane speed. If your theory is able to account for this, I would say most people would agree that your theory is a reasonably successful one. Okay, right. Much of this, of course, depends upon the geometry of the reconnection region, as we saw. If the geometry is more like Petscheck than like Sweet-Parker, then you have a good chance of doing this. It all depends upon the geometry, and the geometry is really not clear in astrophysical situations. Okay, it's only from simulations that one can make some guesses about the geometry. Okay, now the geometry of the reconnection region also depends upon the kinetic microphysics. Okay, why do I say kinetic? Because by the time, like we said, by the time you come down to length scales that are small enough, as small as the reconnection region, the fluid approximation breaks down, and you really need to start worrying about kinetic effects. Okay, so this is the thing, and so the takeaway message is that the physics of the reconnection region, if you will, not off, maybe in the reconnection region, almost certainly involves kinetic microphysics. Okay, involves particles. Okay, either particles explicitly or distribution functions. Okay, it almost certainly does. So reconnection is yet another one of those things where you are forced to sidestep between fluids, between the macroscopic fluid theory and kinetic microphysics. Okay, so when we meet next, we will take up some observational examples of reconnection. I will show you some spectacular movies of solar flares and of coronal mass ejections. These are spectacular eruptive phenomena which are thought to be enabled by reconnection. So that's it for now. Thank you.